The Java ForkJoinPool is a special kind of thread pool which makes it easier to break down a big task into smaller subtasks which can be executed in parallel. By breaking up a task into smaller subtasks, these subtasks can be executed by different threads, as illustrated here. When executed by different threads, the tasks can be executed by different CPU cores, as illustrated down here. This way, a big task can be split up into smaller subtasks which can be executed in parallel by different threads on different CPU cores. Even if the subtasks end up being executed by the same CPU core as illustrated here, it can still sometimes be beneficial to execute them using different threads. For instance, if the tasks perform blocking I/O, then when one thread is blocked in an I/O call, the CPU can switch to execute another thread in the meantime. And even if all the subtasks perform blocking I/O calls, they probably won't be doing so at the exact same time. So you will most likely still be utilizing your CPU better this way. When the ForkJoinPool executes a task, the task can choose to divide itself into smaller tasks, which are then also enqueued in the ForkJoinPool for execution. And you can see that illustrated here. The division of a task into smaller tasks can be done recursively, meaning a subtask can also divide itself into subtasks, and these subtasks can also divide themselves, etc., etc. And you can see that principle over here. You have the main task here that divides itself into two subtasks, and each of these subtasks divides itself into another two subtasks. So we have 4 subtasks in total. The work parallelization process supported by the ForkJoinPool is called fork and join, and it consists of 2 phases. The first phase is the fork phase, and during the fork phase, each task divides itself into smaller subtasks, possibly recursively. And this is what is illustrated here and what I have also shown you earlier, right? So you submit a task to the ForkJoinPool, and that task can choose to divide itself into a set of subtasks, and this can happen recursively until finally the subtask gets so small that it does not make sense to subdivide the task anymore. The second phase is the join phase, and during the join phase, each task joins the result of their subtask together and return the result to their parent task. So in this case here, this task here would join all the results from each of these subtasks into a single result. Over here, the joining will happen recursively because the division, the forking of the subtask happened recursively. So this subtask here will join the results from these 2 subtasks and pass it on to this task up here. And the same thing happens over here. The root task here will join the results of its subtasks, which again have joined all the results of their subtasks. So the root task will actually join all of the results into a single result, which it returns to the ForkJoinPool. And the ForkJoinPool then returns that result to the code that submitted the root task to the ForkJoinPool. As mentioned earlier in this video, the Java ForkJoinPool is designed to help you utilize the CPUs in your computer more efficiently. And in order to do that, the Java ForkJoinPool uses an algorithm internally called work stealing. And I will explain that just now. If you first imagine that you have a situation here where you have 2 threads in a ForkJoinPool, and each thread has 3 tasks queued up for them. Now imagine this task here, the red one, takes a lot longer than these yellow tasks here. What could end up happening is what is illustrated here in situation 2. That thread 2 finishes all of its work and is now idle, while thread 1 is still working on the red task here and still has 2 yellow tasks queued up for it. What the work stealing algorithm then allows thread 2 to do is that it is allowed to steal work from the tail of the queues of other worker threads in the ForkJoinPool. So in this case, thread 2 is allowed to steal this task and start processing it, because thread 1 is still busy with this red task here. Now, if there was only one CPU in the computer, or only one CPU core, maybe this might not be such a good idea. But if you actually have multiple CPU cores, and a lot of computers have that today, then while this thread 1 here is running on one CPU core, then thread 2 can steal some work from thread 1's work queue, task queue here, and start processing that using another CPU core. Now, in practice, you also run into other challenges about, perfect utilization of the CPU core. So you will probably never hit like a completely 100% efficient use of them, because there are such issues or such factors that play into this, such as whether some modern desktop CPUs have performance cores and efficiency cores, and performance cores are typically able to run faster than efficiency cores, but they also use more power. So if CPU core 2 here is an efficiency core, maybe it will actually process some of the tasks slower than thread 1. And then what are you trying to optimize for? Well, here it's execution speed, but what if you wanted to optimize for power usage? Well, then you actually wanted more tasks scheduled on CPU core 2, and I think the ForkJoinPool is not able to take power consumption into consideration when scheduling tasks. There are also other issues, such as many CPUs and CPU cores being boostable, meaning they can temporarily increase the clock cycle frequency, and thus run faster for a while, but then after a while they start to run hot and they have to slow down the frequency again in order for the CPU core to cool down. So there are such factors that play in, but all in all, work stealing still helps divide the tasks more evenly among the CPU cores, so that tasks get executed faster. Now let us have a look at a code example. And the first thing that we want to see is how to create a Java ForkJoinPool. And there are two ways to create a Java ForkJoinPool. And the first one is to simply call the factory method here in the ForkJoinPool class, called CommonPool. This returns a shared ForkJoinPool that all of your application code can use and share. So you don't have to create and manage your own ForkJoinPool. You can just access this one that is shared here. And this one will attempt to tune its parallelism level to the number of CPUs available in your computer. And the other way to create a ForkJoinPool is to create one yourself using the ForkJoinPool constructor here and the new keyword. And then you pass a number here, which is the parallelism level, to the ForkJoinPool, and that is the amount of threads that it will attempt to have running at the same time, processing work. Now, it may not hit exactly this number for various reasons. And for instance, it can be that you have submitted a lot of work to the ForkJoinPool. Maybe it will increase parallelism a little bit just to avoid having too many threads, for instance, being blocked, waiting for blocking IO to finish, and such similar things. But so this is just an indication to the ForkJoinPool of how much how much parallelism that you would like it to attempt to achieve or to use. Second, you can see that this code example here creates a recursive action and a recursive task, and both of them are submitted to the ForkJoinPool. And in this case, I'm just submitting it to ForkJoinPool 1, but it doesn't really matter if I submit it to ForkJoinPool 1 or 2 for the sake of this example. The difference between a recursive action and a recursive task is that a recursive action does not return any result. So perhaps it's just writing some data to the file system or updating a database or something else. Whereas a recursive task does return a result, and you can see that this result here is returned from the invoke method that submits the task to the ForkJoinPool for execution. And then here at the end, this result is simply printed, and then the application sleeps 1000 milliseconds, and that is, you can see it's just a thread sleep millis. And this is not actually necessary in a normal application, but it's just for this code example here, it's necessary because I experienced that sometimes the system out print lines from inside of these actions and tasks here, they did not actually make it out into the console before the application shut down, and so it was hard to see if the application was running correctly or not. But by adding this little sleep period here, then all of these system out print lines, they actually do make it out to the console before the application shuts down, and you can see that the application actually runs as expected. Just to recap, a recursive action does fork itself into smaller subtasks and can do so recursively, but it does not do any joining of the results because a recursive action does not return any result back to the caller of the or the submitter of the task or the action to the ForkJoinPool. A recursive task, on the other hand, does have both a fork phase and a join phase, because a recursive task does actually return a result, and thus the subtasks also return a result that is then joined up in the parent task. And this can also happen recursively as illustrated here. So a recursive action only has the fork phase but no join phase, and a recursive task has both the fork phase and the join phase. Now let's have a look at the myRecursiveAction implementation, and as you can see, the myRecursiveAction class extends RecursiveAction, which is a class that comes with the Java util concurrent library of concurrency utilities. And you can see here that internally it has a variable called workload, and it has a constructor here, and it takes a workload parameter, and then we set the workload, this member variable here, to the workload passed as parameter to the myRecursiveAction constructor. And then this class has a single method here, which is overwritten. It is a method that is overwritten in the RecursiveAction class. It's called compute. And if you want to implement the recursive action, then you have to override this method. And what this method does is it first checks here if the workload is larger than 16. And if it is, then it prints here that it will split the workload into 2 parts. And as you can see, it also splits the workload so that it first divides the workload in 2, and that becomes workload 1. But remember, this is an integer division, so there might be a remainder if this is an odd number. And so the second workload here is then the original workload of this recursive action minus the workload for the other here. Then we avoid any remainder getting lost. So if this was 3, or actually let's say just 21, then this here would be 10, and this number here would be 11. Then it creates 2 new workloads, and you can see the number for workload 1 and workload 2 are passed as parameters to these recursive actions. So I said it created 2 new workloads, but it does actually create 2 new recursive actions. And then it calls the fork method on these 2 recursive action instances. And this is also a method that is inherited from the recursive action class, and this will submit these 2 recursive actions to the ForkJoinPool that is also executing this instance here of the recursive action. And that's pretty much it. And if the workload is not larger than 16, it simply prints out that it's doing the work itself, and then it prints out the workload. Now, this implementation here does not actually do any work. The only thing it does is it pretends to do some work. And this work, the size of this work, is represented by this workload number here. But you could imagine this, instead of a workload simply being a number here, you could have had like a list of objects to process, or files to process or write or read or whatever, right? And then it would be checking if there were more than 16 objects in the list. It would split the list in two and then pass each half of the list to another sub action here, and then enqueue them for execution. So that's pretty much what a recursive action looks like. And as you can see, there's a fork face down here. Or actually, the whole face here is part of the forking face. The whole code block here is part of the forking face. But there's no join phase anywhere. Now let's just try to run this my recursive action example here. As you can see out here, I have both a recursive task and a recursive action. And I will get back to the recursive task later, but let's first just try to run this part up here, the invoke here, and we just comment out this invoke here. And we also comment out the print of the result, because it comes from this line here, which we just commented out. And then we try to run and see what happens. As you can see, we start with a my recursive action with a workload of 123. This is broken into two subtasks here. We have 61 and 62 and 61. And this is broken into a task of 31 and 31. And this one here is broken into 16, 15. And here again, you see 16 and 15. This 61 here is broken into 30 and 31. And then you see down here 15, 15, 15, 16. And this 16 here belongs to that one. So as you can see, the breakdown of the task is taking place until the point where the workload reaches a value of 16 or lower, and then it just stops breaking it down at that point. And the reason it stops breaking it down at that point is simply that there's a certain amount of overhead associated with breaking a task down and having the threads communicate about its execution. So if you break it down into two small tasks, then that overhead becomes very big compared to the total time it takes to execute all of the subtasks. So at some point, if you break the task down into two small tasks, you will not really get any benefit anymore. So beware of that. And in this example here, I decided just completely fictively that at the workload of 16, that's, when I no longer want to break it down into smaller tasks. Now let's have a look at a recursive task implementation. And I've made one here. It's called my recursive task. It extends the recursive task class instead of the recursive action, which extends the recursive, or my recursive action, which extends recursive action class. And the recursive task class has both a fork and a join phase, because it is actually able to return a result. But most of the class is almost the same as the recursive action. You can see I'm using a workload number here, which is simply some way to represent some fictitious load. And as you can see here, we have the fork phase. And what it's doing here is it's checking if the workload is larger than 16. Then it simply splits the workload in two and creates two new recursive tasks and call fork on them. This is exactly the same as you saw in my recursive action just before. But here comes the join phase. What it's doing here is creating a local variable called result, and it's simply adding to result the return value from subtask 1 and subtask 2 join methods here, and that will cause these will method call will block until these two tasks have been executed. And once they return, that means these subtasks have been executed, and then the result is added up together and returned. And if we just look at the chart here again, that means simply that some of these tasks here will, like this task here, it will fork into two, and then it will try to get the result from this subtask and from that subtask, and it blocks until both of them are executed, and then it adds the result up and returns that to this task, which eventually returns it back to the fork join pool. And what you can also see here is that in case the workload is not larger than 16, then it is just doing the same thing as in my recursive action. It is simply returning workload times 3 and saying, I'm just doing the workload myself. There's no reason to fork the task into smaller tasks now, because I have maybe not explained that, but there is actually a little bit of an overhead involved in forking a task into two tasks, and all the thread communication that is going on when you fork it and then join the results. So don't create too small tasks, because once you get to too small tasks, then you may not actually have a benefit anymore. But other than that, the myRecursiveTask class is very similar to the myRecursiveAction class. And as you can see here, I've modified this Java ForkJoinPool example a little bit. Instead of invoke with the action, it invokes with the task. And now I try to run it, and then we see what happens here. And as you can see, it is like we expected it to. It starts with a workload of 123, splits it into two subtasks of 61 and 62, which I again split into 30 and 31 and 31 and 31, and these are further split, etc., etc. And here's the final result. That is the results that are returned and joined up from all the tasks and subtasks, as returned here and as calculated and returned up the chain here and here. I will not be covering every single method of the fork join pool in this video, but there is a handful of methods that I would like to talk a little bit more about, because they are good to know that they exist. The first method here is the submit method. And the submit method is an alternative to the invoke method, where the invoke method blocks the calling thread until this task that you are submitting has returned a result. The submit method does not block. It returns this fork join task, which is a representation, or like a handle, a reference to the task that you have submitted. And once you have submitted the task, you can go about and do other things here if you wanted to. Right now we're not doing anything else, but like at this point here you could do something else, and then at some point when you're ready for processing the result, you can call the fork join task get. And in case the task has finished executing, then you will get the result immediately. And if the task has not yet completely finished, then the call to get will block the calling thread until the task has completed executing totally or completely. Then there are the methods get and set parallelism, and these will the get parallelism will of course just return the number that you have passed to the fork join pool during its creation, or that you have set by calling set parallelism. And the parallelism level is just some kind of target for the fork join pool, or of parallelism that the fork join pool should attempt to achieve. And it might the real number might be different. If you submit a lot of work to the pool, it might grow itself a little bit beyond this number. So it's not like a guarantee that it will always create 10 threads, but this is like a target set of threads that it should keep internally. The get pool size returns the actual number of threads that your pool is using. The get queued submission count here returns the number of tasks that are currently queued up inside of the fork join pool. The get running thread count here will return the number of threads in the fork join pool that are currently running and executing a task. And so idle threads are not counted in this count. Fork join pool is shut down will return true if the fork join pool has been shut down. And the is terminated method is the same. It will return true if the fork join pool is terminated. I'm not actually sure what the specific semantic difference is between these two methods. And then here is the is terminating method returns true if the fork join pool has been told to shut down but has not yet completely terminated. And then there's the shutdown method and the shutdown now method. The shutdown method will tell the fork join pool to shut down, and what the fork join pool will do then is it will try to execute or finish all the tasks that are currently queued up inside it, and it will reject any new jobs or tasks that you try to submit to it. Those will just be rejected with an exception saying that the fork join pool is shutting down, so you cannot submit any more work to it. But whatever has already been submitted will be executed and finished. And the shutdown now method will simply try to shut down the fork join pool as fast as possible, meaning whatever is currently executing might be finished, but whatever is queued up that has not yet started executing will not be executed. It will just be ignored. And those are pretty much the most interesting, most important methods that you should know about in the fork join pool. There are more methods, but you only really need them in specific for very specific use cases. So I would encourage you to look at the Java doc to learn more about those methods. That is all for this video about the Java fork join pool. Remember to check out the description below this video for links to a textual version of this tutorial, as well as other related tutorials about Java concurrency in general. And if you like this video, please hit the like button. And if you would like to watch more videos like this, please subscribe to my channel.